thanks to UP Travel for sponsoring this video. The ground was moving on and off for millions of years. The Earth shifted and crumbled as enormous pieces of volcanic rock were shoved thousands of feet into the sky. This was the beginning of something new, a different continent, a different landscape, one rich with the beginnings of waterfalls and rich with shining metal that would help build a nation. Eventually, because this is the story of Michigan's Keweenaw Peninsula, just over 1 billion years ago. But 1 billion years is a long time, so how do we know any of this? How do you piece together the clues to understand something that happened before the first animal even walked the earth? It's story time. This story is the tale of the Keweenaw Peninsula, a bit of land in almost the farthest northwest corner of the state. And it has quite the scar running down its middle. Up and to its left is cooled lava from a time when an earlier continent was slowly being torn apart. Down and to its right is sandstone, cemented grains of quartz and feldspar eroded from once mighty mountains you can still see the remnants of in the distance. All throughout the Keweenaw, you can find this lava rock rising above you. But this is actually a little weird, because here's the thing. This lava rock is older than the sandstone below it. And normally in geology, you'll find the older rocks underneath young ones, having been buried by their newer counterparts. This is called the law of superposition. So what happened here? And also, why does it matter to us all these many years later? Well, one of the best places to find answers is here, at Houghton-Douglass Falls, Michigan's tallest waterfall. What's a little wild about this video is that I've been working on it for 4 years, which is almost as long as this series has been around. Back in 2022, I got an email from someone who was a bit of a legend in my mind. Dr. Bill Rose, a professor emeritus at Michigan Technological University. See, Dr. Rose wrote these incredibly informative web pages all about geology in the Keweenaw, and some of the first real videos I ever made in this series were directly inspired by his work. So I was a little starstruck when he emailed and asked if I would be interested in talking with him and 2 other researchers about a story they thought was worthwhile. One was Dr. Erica Vai, who I'm currently working with on another Keweenaw project, and the other was Dr. Jim DeGraff, who you might recognize from my video about the Huron Islands. Back in 2022, Jim took me on a tour of Houghton-Douglass Falls, and I was all ready to use that footage to make a new video when I talked to the DNR, the Michigan Department of Natural Resources. See, the DNR manages this site, but 4 years ago, they hadn't had time to make it suitable for the general public. There was no official trail, no safety signs, no good place to park, nowhere to put your garbage, so the DNR wasn't keen on the area getting a ton of publicity. Now, to be fair, there are tons of places like that across the Upper Peninsula. Places with no guardrails or trash cans or concrete. But in this case, it seemed like the responsible thing to do was to wait a hot second while the DNR made the site a little more accommodating. So, a few weeks ago, Dr. Jim DeGraff and I showed up at the brand new Houghton-Douglass Falls parking lot. A little older, a little wiser, and with better videography skills. It was finally time to get to the bottom of this. Houghton-Douglass Falls, which has been called other things throughout the years, has been studied by geologists for the better part of 200 years. Notably, in the 1880s, a couple of scientists from the U.S. Geological Survey named Irving and Chamberlain were out here, and they were trying to answer the same question we are today. What's the deal with the scar on the Keweenaw? One idea they wanted to test was that, well, nothing was strange here. Previous geologists had proposed that the sandstone was actually the older rock, and that the lava flows had come later. But today, largely because of Irving and Chamberlain's work, we know that's definitely not the case.
So if you look across over on the other side there, you'll see near the top, maybe the upper half or so, the rock is breaking out into these big blocks, and the color is a little different. If you follow that down, there's a boundary, and below that boundary, the rock is a little bit more orangish, and it breaks up into smaller blocks. So that's the boundary, we think, between a lava flow above and the top of a lava flow below. And we think that lava flow above is called the Copper City flow because it can be traced from here all the way up to Copper City and beyond. And the Copper City flow has been dated, and it is 1,093 million years old. So it's dated pretty precisely by two different investigators. So there's agreement between the two different investigators.
And is the reason that the top of the flow is more like broken looking or like discolored, is that related to anything? Because I know like the tops of flows are more bubbly.
Correct. Yeah, they're more bubbly. In geology speak, they're more vesicular or amygdaloidal. So vesicles are gas bubbles that get frozen into usually the upper part of the lava flow. And if those gas bubbles become filled with minerals, we change the name for some reason and we call them amygdules instead of vesicles. Yeah, because we have to have a new name for every minor difference in the geology. Yeah. And also the upper part of a lava flow, before the next lava flow is deposited on top of it, it's exposed to the atmosphere and weathering, right? So, I mean, that was actually the surface of the Earth at one point. So it got rained on, it got oxygenated or oxidized. And also the gases that were escaping from the lava flow, because, all magmas have some degree of water vapor and carbon dioxide and other vapors that escape when they come to the surface, and they rise because they're light, and they interact with the upper part of the lava flow in the atmosphere to create this oxidized look. That's why usually the top of a flow has this more reddish color.
Okay, cool. Yeah. That makes sense.
And then as the flow is moving, you've probably seen videos of like the lava flows in Hawaii or Iceland.
Yeah.
The upper surface solidifies and gets hard, but underneath, lava is still moving, so the upper surface will get kind of moved around and broken and fragmented. So you often get these little fragments that are broken up and they get tumbled on the surface. And so often, that is expressed as this sort of smaller scale blocks that you see up at the top of the lava flow.
Cool, thanks.
So that's the next place we could go to, is right at the top. We can walk down and get not dangerously close, but we can get pretty close to look at those features right at the very top of the main fall here.
Cool.
We are probably within the Copper City flow, getting close to its top. The top is going to be upstream, but the Copper City flow it's the thickest lava flow near the bottom of the Portage Lake Volcanics, and that's why it's possible to date it, because the thicker lava flows cool more slowly, and as they cool slowly, the crystals get bigger and bigger, and it takes a lot of time for a thicker lava flow to cool, so you get certain elements like zirconium that are left behind, and then eventually they crystallize into zircons, and zircons are grains that are highly valued by people who date rocks because they have radioactive uranium in them. And we know the rate at which that radioactive uranium breaks down into various daughter products and eventually becomes lead. And so by analyzing the amount of uranium and lead isotopes in the rock, and then knowing the rate at which the uranium that's radioactive decays eventually to lead, it's possible to calculate the age.
If you'd like to learn more about uranium-lead dating, I recommend checking out my video about the waters meet gneiss, which goes into that in more detail. I'll include a link in the description. But Jim gave a great summary. Different types of uranium turn into different types of lead at very predictable, well-known rates. So if you compare the amount of uranium in a zircon crystal to the amount of lead, you can figure out how old it is. And that's what geologists have done with the Copper City flow, putting it about 1.093 billion years old, or 1,093 million. Meanwhile, the sandstone on the other side of the Keweenaw Scar, it's called the Jacobsville sandstone, and it's younger than the Copper City flow. More specifics later. So, for some reason, in many places, the older rock is above the younger one. Why? Now, if you've been watching this series for a bit, or if you know something about geology already, you probably already know the basic answer here. The Keweenaw Scar is a fault. It's a break in the earth where, in this case, one piece of bedrock was shoved upward and over another. Faults are really common in geology, but think about what this means. This means that something so powerful happened here that it managed to push bedrock on one half of the peninsula up and over the bedrock on the other half. In a series of movements that likely lasted millions of years, the volcanic rock shifted between 4.5 to 6.5 miles relative to the sandstone on the other side. And it's possible that this came with millions of years of earthquakes. In textbooks and in animations like this, movement on a fault often looks so clean and tidy, but this doesn't capture the dynamics, the energy it took to make this happen. And if you know where to look at Houghton-Douglass Falls, you can start to see just how powerful the movement on the Keweenaw Fault really was.
Now we're at the bottom of Houghton-Douglass Falls. You can still see the boundary between the kind of the darker rock that breaks out into these larger pieces, and then below it, the more reddish gray rock that breaks out into the smaller pieces. So that is, we think, the bottom of the Copper City flow and the top of the next flow below. Can you see these surfaces that are kind of smooth and polished,
Yeah.
like you see there? So, these are surfaces along which the rock has broken and has been sliding. And so you get these polished surfaces that have various alteration minerals like chlorite, hematite. These are indicators of just the shearing motion of these little blocks that have been broken up in the fault zone. And then as a result of the fault moving, these blocks have also moved one relative to another over time. So all of these pieces here have these polished surfaces. Sometimes you actually see parallel lines on there. We call those slicken lines. And we can measure the orientation of the slicken lines to see which way the blocks were moving. But pretty much all of these pieces here that come from this little chute that continues up the slope up to where we were near the top, this is all brecciated rock that's been sheared, and it's part of the fault zone. Yeah, you can kind of see the little bit of the lines there if I get that in the light.
Yeah, kind of they're like orange or a little redder.
Well, okay, I'm looking at, so there's, those are lines, but I'm looking at the lines that are going like that direction there.
Sure,
Right,
sure, I
yeah,
see.
Yeah. The orange ones are steps that are perpendicular to the more subtle ones that are running in this direction that I'm pointing out.
Yeah.
And so by looking at the nature of those steps relative to these slicken line, it's possible to determine what direction the missing block, which is the one that would have been sitting on top of this, was moving. So in this case, the missing block would have been moving in that direction. But we don't know, how this was oriented right now. It's just a loose block, right? So,
Yeah.
that information on a loose block isn't very helpful, but if you find that same type of structure in a rock that's still in place, then you can make a measurement and you can use that to say something about how the rocks were deforming when the fault was active.
Cool. Now, at this point, I should probably mention the cave, which isn't a cave at all, actually, but an adit, a horizontal entrance to a mine. The Keweenaw Peninsula has an incredible legacy of copper mining, which I've talked about elsewhere. Hundreds of millions of pounds of copper were deposited in these various layers of rock, and the Keweenaw Fault likely played a role here. One idea is that the forces that made the fault also made other faults and fractures, and those acted as highways for copper-rich fluid from deep underground to reach the surface. Another idea is that the copper was deposited lower, and then movement on the fault shoved those copper-bearing rocks up where we could find them. And, of course, both might be true in some way. So for literally thousands of years, people looked for signs in the cliffs that there might be copper hidden within.
That adit was an exploration adit for copper by the Douglas Houghton Mining Company. So not to be confused with Houghton-Douglass Falls. So Douglas Houghton Mining Company was named after Michigan's first state geologist, Douglas Houghton, who came here in the late 1830s after statehood and did a survey of mineral potential and reported back that there was significant potential for copper mineralization along the Keweenaw Peninsula. And that started the copper rush of 1843. So the mining company that excavated that adit was organized in 1845. That's 2 years after the beginning of the copper rush. And they probably dug that adit sometime 1845, certainly before 1850. So it's before the Civil War. And they had seen copper in some of the veins here. In fact, the student that I worked with and I took some samples from a little bit downstream and also at the base of the falls. And there are little flecks of copper in some of the veins, the quartz veins. And they did discover some copper in that adit, but it wasn't of sufficient quantity to make it worthwhile to develop a mine. So the company didn't last very long and they moved on to other things. But I've been into the adit. It goes in about 120 feet. It goes in and then turns a little bit to the left and then takes a sharp right turn. But the end of the adit is actually underneath the very top of the waterfall that you see here. So it kind of goes in, turns left, turns right, and it ends up almost directly below the top of the waterfall.
As of the time I'm filming, there are currently no signs up about the adit, but it is not part of the official trail and is not intended to host visitors. The reason trails exist is to keep people safe, but they're also to prevent erosion, protect plants and wildlife, and keep the site working in a healthy way so that people can enjoy it forever. For those reasons and others, I did not go into the adit, even though Jim is very familiar with the site and would have been able to direct me safely. But going back to the fault, we saw that little section where the rock had been polished and scraped. But the Keweenaw Fault isn't just limited to that small stretch. It's much more of a fault zone than a single surface. And that's a big part of why this waterfall exists in the first place.
Right here, we're standing on Portage Lake Volcanics. The rock is broken up. It's going to be broken up almost all the way to the adit, and at about the adit, that's where the rock starts to go back to being intact and less brecciated. So we're basically standing in the fault zone, and the fault zone continues to about the adit or about the base of the waterfall. So the reason that waterfall is there is because that rock is a lot more resistant. It hasn't been broken down by the fault movement. Being more resistant, it tends to resist erosion by the Hamel Creek, which is flowing down through this valley. The more resistant part stands tall. Getting down here where the rock is all broken up, it's eroded more quickly, and the Jacobsville sandstone downstream erodes even more quickly. So it's that difference in contrast between the resistance of the rock to erosion that creates the waterfall. And that's true of almost every waterfall anywhere in the world. It's the contrast between the resistance of the rock at or above the waterfall to the rock below the waterfall.
Cool. So here, but it's like, it's all lava flows, but the difference is that the fault zone, because it's broken up, is more susceptible to erosion versus the more solid parts.
That's correct. And then also downstream, you've got rock that is even more easily eroded, the Jacobsville sandstone. Yeah.
So the clues are starting to come together. You've got older rock lifted above younger. You've got rock layers that are tilted. You've got sections of rock that are broken up and polished and scraped. But there's one more clue I want to show you that really proves just how powerful this event was. And also, it's honestly one of the best demonstrations I've ever seen. So truly, hats off to Dr. Jim DeGraff.
let's just look at this a little bit. To your right,
Okay.
I'm going to quiz you, and then you can
Excellent.
see, like, if you see what I see.
Sure.
If you look at this outcrop here,
Okay.
describe for me the layering that you see.
Yeah.
I guess that's really the quiz part of
Okay.
it.
Okay, so there's a top section. It seems like a little ways down, there's a section of like very thin layers.
Yep.
Looks like sandstone. Larger section below that looks a little bit more cemented together, and then maybe more breakage at the bottom.
And then maybe at the top, show me with your hand, like make your hand parallel to the layers, which way you think the layers are going.
This is where I'm struggling, because like this one's a little bit curved at the top, but I think it's predominantly maybe sloping that way. Or this way. You know that saying, you can't see the forest for the trees? Yeah, that was me. Because while I was focused here, the true answer was staring me in the face.
The Keweenaw Fault is this red layer, and the fault we crossed several hundred feet upstream to the northwest, and it's dipping about 20 degrees, so it's dipping about like this. And we are currently somewhere down below the fault in the Jacobsville sandstone that originally had horizontal layers. So this is one layer in the Jacobsville sandstone. And at this location, we are about 200 feet below where the fault would have been. So a lot of material has been eroded from above us, but if that material had not been eroded and we could get into this position, the fault would be about 200 feet over our head. If you think about what it takes to move a large mass of Portage Lake volcanics up an inclined ramp like this, it's a tremendous amount of force. And that force is pushing horizontally on the Portage Lake volcanics, but it's also pushing horizontally on the layers of sandstone underneath. And then as the Portage Lake volcanics are sliding up the ramp, they're also tending to drag the layers of the sandstone below up along the underside of the fault. So I'm going to put the fault down now, but just it's still there. So if you think about that motion and the effect it has on the underlying sandstone, so I'm going to push and I'm going to raise the one side and keep that flat. So the vertical wall here is what lies over in this direction to the right, and the horizontal portion is what lies behind me. So this is what we're looking at here. It's an asymmetric fold where the layers that were once flat have been squeezed horizontally, and the side to the left has been raised up because of the action of the fault to produce this fold. So we call this an anticline. Probably this happens all over the region here, but we don't see it very often because of the soil cover and the vegetation. But this is a particularly good example, this type of deformation that occurs in the footwall of the Keweenaw Fault.
Honestly, that was just a masterclass in science communication. So, where does that leave us? 1 billion years later, we can see clues that tell us something dramatic happened here. Something slow but powerful, enough to push the Earth on one side of the Keweenaw Fault thousands of feet over and above the other side, to break rock and deform the Earth's surface and change this region forever. But what was that event? Turns out, it didn't happen anywhere near the Keweenaw Peninsula. The details are up for debate, but the general consensus among geologists is that all this movement on the Keweenaw Fault was driven by processes happening out east, in what's now the general Appalachian region, but a long time before the Appalachians were a mountain range. There, about 1 billion years ago, two continents were colliding with each other to form an even older mountain range. This is called the Grenville orogeny, and it was a relatively slow event. The orogeny seems to have happened in at least 2 phases, and each was around 30 to 60 million years long. But the end result was millions of years of pressure that was felt all the way out here in the Midwest. And one way or another, those forces over that length of time were enough to drive the Portage Lake volcanics high above the Jacobsville sandstone. Again, the details are up for debate. The exact nature and timing of the movement on the Keweenaw Fault has been hard to pin down, in part because geologists are still trying to figure out exactly when different sections of the Jacobsville sandstone were deposited. The formation is thousands of feet thick, and it's not yet clear how old the lowest layers are. But the key thing to know for this story is that at most, the upper layers are around 992 million years old, and some could be younger. And if any of those layers were deposited after the Grenville orogeny, that could mean that some movement on the Keweenaw Fault also came after that event. It's a little messy, but the theme is the general timing, the direction of Keweenaw Fault movement, and the way the Lake Superior Basin is squished are all consistent with the Grenville orogeny, providing the main driving force about 1 billion years ago. So, how do you uncover something that happened before animals walked the Earth? In short, you look. You take countless samples. You study the minute details and compositions of every rock and rock layer, while also keeping your eyes open for the big picture. You date zircons when you can find them, and overall, you don't rush. I started making videos about the Upper Peninsula because I came across Dr. Bill Rose's writings about the Keweenaw. The first 2 videos I made were about waterfalls and Jacobsville sandstone. So in many ways, the Keweenaw Fault is kind of the reason this entire series exists in the way it does. It took 4 years for the conditions to be right to make this video. And in that time, Dr. Rose actually passed away just last year. But I do hope he knew how much of an impact his work had on the people and the communities around him. And I hope you'll think of him fondly if you ever find yourself at Houghton-Douglass Falls, or really, if you ever find yourself enjoying the geology anywhere in the Keweenaw Peninsula. As always, thanks for being here. And special thanks to UP Travel for sponsoring this video many years in the making. You can learn more about visiting Houghton-Douglass Falls and the entire Upper Peninsula at uptravel.com and by following them on social media. I hope you learned something that makes you think about the world just a little differently, and I'll see you soon.